My name is Greg Clifford. I'm the Manufacturing Segment Manager for Cray. I have a worldwide responsibility for automotive, aerospace, and manufacturing in general within Cray. So manufacturing encompasses a broad range of industries, primarily the automotive and aerospace industries. It also includes consumer products, tire manufacturing, heavy industry, really any company that's producing a product. I guess one thing that ties all of these segments together is the use of CAE application codes for simulations in the product design and also the manufacturing process. Well, in automotive, crash simulation tends to be the dominant simulation field. So LS-DYNA, PAM crash, Radius, Abacus are typical applications being used there. Computational fluid dynamics would be the next biggest consumer of high-performance computing cycles, Fluent, Star CCM+, and then just structural analysis in general, whether it be NVH using Nastran or OptiStruct, or stress simulation with Abacus, ANSYS, and so on. In aerospace, computational fluid dynamics would probably be the #1 application area. A lot of in-house codes are used here, but also, again, you see Fluent, Star CCM+, and so on. And in other industries, it's really the entire spectrum. So if there's one thing that ties all of these industries together, it's basically the same set of application codes being used. Well, about 10 years ago, the manufacturing segment or the CAE application segment made the transition to MPI parallelism. And about 5 years ago, the typical MPI job was running using a few dozen cores, depending upon the simulation. 32, 64 cores was typical. What we're seeing now is the push towards much higher levels of parallelism, up to 128-way, 256-way is quite common, and more we see the request for thousands of cores per simulation. For the manufacturing segment today, automotive and aerospace, they're really moving towards CAE-driven design, so using simulation as opposed to physical testing in the design process. The first component of this is much higher fidelity simulations. So for automotive crash simulations, we're seeing 5,000 to 10,000 elements per simulation. Computational fluid dynamics, hundreds of millions of cells, moving towards 1 billion cells for each simulation. So this really ramps up the requirements for scalability to get the turnaround for these individual jobs. The other component of this is ensemble analysis, so design of experiments or stochastic simulations, where you want to run not a single job, but dozens, really on the order of 100 jobs to fully explore that design space. And both of these things, higher fidelity and ensemble analysis coupled together, are dramatically increasing the requirements for compute power and specifically high-performance computing simulation. Well, the industry in general is moving more towards predictive simulation, where you're using computer simulation to actually predict the performance of a product as opposed to just analyzing it after the design. An example of what's making this more complex is the introduction of new material models. So you have aluminum being used much more, composite structures, honeycomb material. All of these things are new to the industry, and they require a lot more simulation to fully understand their behavior. On top of that, you now have, of course, a very competitive environment in general, shorter design cycles, and computer simulation is really the only way to address this. Physical modeling, just physical testing, just cannot meet the requirements of the industry today.